The fifth lecture in our climate change series is going to be about carbon sinks, greenhouse gas sinks. So climate change, number 5, sink. Another word for that that's maybe used a lot in the news or in the literature is sequestration. How can we sequester and remove greenhouse gases from the atmosphere? We're going to start off with a graph. Graphs are super informative for understanding scientific process, for quantifying scientific things. And so here's going to be CO2. Now we're going to do this without numbers. I snagged this from a source that did have numbers, and you'll be able to find that if you need to. And here is time in decades. The amount of CO2, CH4, other greenhouse gas emissions have increased over time. Do you remember what number that is that we're currently at? 59 gigatons. Well, the amount of CO2 that has been sunk or sequestered by natural processes has also increased over time. Even though we're adding more to the atmosphere over time, the natural processes are actually also removing it. So this would be our graph for sinks. Both are increasing. That might be a point I want you to, we could do star. Both are increasing. All right, that's good. But the sinks end up only matching about 50% of emissions. All right, so emissions are outpacing the sinks by about 50%, and that's why greenhouse gases are accumulating in the atmosphere. So let's talk about these 5 processes that actually are doing the good work of stripping greenhouse gases from the environment. Now, I should point one thing out. This is, I guess I made a little bit of a mistake. Greenhouse gas that we talked about with emissions was all emissions. This 59 included more than just CO2, but this graph I did is just CO2. And the sinks and sequestrations we're talking about are just for CO2. So I flubbed up. Maybe we should do this because that number wasn't quite accurate. I think it's closer to 43 is what's just CO2. Anyways, okay, let's get on to our 5 carbon sinks. The very first of the carbon sinks is a biologic sink. This is an elementary school education sink. You can guess what it is. It's biology by photosynthesis. Synthesis. And the reaction, these are going to be simple chemical reactions. We have CO2 in the atmosphere plus H2O plus photosynthesis with the sun is going to produce plant fiber, sugars basically, plus oxygen. And it is this process of, right? Look at this. We have CO2 on one side of the chemical reaction, and on this side we don't. We are sinking it and sequestering it away from the environment. This is going to end up being over 50% of all sequestration is done by photosynthesis. Sequestration. Oh, spell it better than me. My penmanship and spelling is a little sloppier than I want yours to be. This includes, all right, so there's our chemical reaction, here's our statistic, and I want you to include, this is both marine plus terrestrial, so jungles and prairies and algae and plankton, right? All these things together are combining and making things by photosynthesis. And one of the interesting things is, with chemical reactions, if you add more stuff on one side, you tip towards the other. And so as we anthropogenically are adding CO2 into the atmosphere, we're actually increasing the growth of plants. There is a fertilization effect. The other feedback that's going on, so we're just gonna say fertilization, maybe atmosphere fertilization as we increase the CO2. The other thing we're doing is by global warming, we might be increasing the growing season in places. And if we're increasing the growing season, we would also be increasing more amount of time to produce plants. And so these are some feedbacks within this system. All right, the second major sink is going to be a geology sink. The geology sink is the production of fossil fuels. So geology as a sink. And what's here is that the dead organism that has carbon in it, so let's say we've made an organism and it's a plant. That plant has sunk CO2 from the atmosphere by photosynthesis. In fact, we're going to do this. Dead organism that was once alive by photosynthesis. It dies and it gets incorporated into a rock. It gets buried, incorporated into. This could be a fern in a shale. This could be a limestone. This could be a coal. In fact, let's go ahead and put those rocks. These are some of the rocks that do this. Limestone will hold carbon inside of it. So will shale. So will coal. And I'll show, here's a picture. In fact, this picture kind of summarizes both of the previous mechanisms. This is some peat from Britain. And what this peat represents is this grass material, right? All this grass material dies and gets buried and more grass grows upon it until you get this really dense organic material that can be burned. It hasn't yet turned into coal, but it eventually will. So peat to coal would be a good example of a geology sink. That's a simple one. This third one is not so simple. We're going to call this one terrestrial waters. Number 3, terrestrial waters. Most of you won't have thought or heard about this one. I think the easiest way to teach terrestrial waters is with the chemical equation. Before we put that in, I'm going to put this, we're going to say weathering of silica-rich rocks. Many rocks are rich in silica. Things like granite or schist, maybe you've heard about those before. Those are silica-rich rocks. And when you weather them, you actually produce a chemical reaction that will strip CO2 from the atmosphere. Here's the reaction. Simply, we take SiO2. This is our silica-rich rock. Plus CO2 plus H2O, which in a lot of ways is doing the weathering. So if here's one side of the chemical formula, and if we're gonna associate some of these chemical symbols with a word, I want you to associate SiO2 with silica-rich rocks. I want you to associate H2O with the word weathering. Of course, you're associating CO2 with greenhouse gas. And this is good. The reaction that occurs will produce a clay, and it'll be a silica clay, so that keeps us balanced, plus bicarbonate, HCO3 minus. And HC3O minus, which is also called bicarbonate, this is dissolved. We could put the word ion. All right, it's like molecules that are dissolved in water. And so this is just dissolved in a river. And that river flows to the ocean where bicarbonate hangs out and gets stored for long term. So, all right, so okay, we're almost done with terrestrial waters. This is H2O from a river. It turns into clays, which stay put, and bicarbonate, which flows in river to oceans. This is a really powerful sink and kind of a complicated one. Read about it on Wikipedia or the textbook if you want to hear more about it. All right, number 4. There's only 5 of these. Number 4 is somewhat complicated as well. This one's called marine waters. So terrestrial water, that is rivers. Marine water can also strip CO2 from the atmosphere, but this is ocean water. So this is going to be called ocean water, absorbs CO2. And bicarbonate plays a role here. It's a 2-step reaction. In fact, we're going to write it out. We take CO2 from the atmosphere plus H2O. In this case, this is ocean. And we already have some carbonate in that water. That's what this ion is. This is carbonate. Now, carbonate is the building block for limestone. It's the building block for shells and for corals and for plankton. So let's say shells under this. This is a very important thing for organisms. When these 3 things come together, they react to form H2CO3. This is carbonic acid. plus some leftover CO3 carbonate. And this will react to form bicarbonate, which sits as an ion in the ocean water. And all that is good, all that is natural. But if we are adding more here, on the left-hand side of this equation, we're going to drive, right? Anthropogenically, we're driving this chemical reaction to the right, towards more acid and towards more bicarbonate. And let me tell you what, that has produced some problems. And the problem is ocean acidification. Okay, there's actually two issues with this. Let's say it this way, two issues. The first issue is ocean acidification. Oh, there's a lot of long words in science. Ocean acidification. And at this point, the pH of the ocean has dropped 0.1 on the pH scale, which doesn't seem like much, but it's a log scale, so it's a fairly big impact. And the pH of the ocean today, in many places, is lower than it's been in any time in 50 million years. That's a big, that seems to matter. The other thing is the rate at which the pH is dropping. We'll say this rate is 100 times faster than what is happening in nature. So this is a big change that's impacting organisms for the most part. And if one organism is affected, others are too because of the food chain. The other aspect, besides ocean acidification, which is this carbonic acid, okay, that's one, is the drop in carbonate. So we're going to say reduce CO3 to minus, which makes it harder for organisms to produce their body parts. Reducing CO3 equals harder to make body parts. Specifically for things like shells and plankton. I mean, jellyfish and seagrasses actually love this. It makes it easier for them to live. So it's an adjustment to the ecosystem. Whether you're pro shells and plankton or if you're pro jellyfish, we can all agree that it changes the ecosystem. The last of our carbon sinks is going to be our human sinks. We are trying with human technology to take greenhouse gases, specifically CO2, and sequester them by, maybe we could call this geoengineering. It is a new field. It is very well funded because there are a lot of institutions and governments that are concerned with climate change. And so the goal of this human technology is to capture / sequester CO2 for a long term from the Earth's atmosphere. There's a lot of different technologies that people are using to do this. Here's one. I think this is a picture from a place in Iceland. And what we can see here is a bunch of fans. This is called direct capture. And these fans are sucking wind. Okay, they're sucking wind in, and there's filters in there that are trying to strip CO2 out from the atmosphere so that when the air comes out the backside, there is like no CO2 in it. I don't know if this can work. Maybe if we put every Walmart fan across our planet on with these filters, we can make an impact. I don't know. Another human technology that we're trying to do is called a carbon credit. This is an economic driver. Carbon credit. This is where you can get money for sequestering carbon, and governments or other institutions will pay you to do it. I don't know if it's a crock or if it's real. But one thing I do know is that money makes things happen. And so whether it's working well now or not, maybe this free market economy concept is a way to push CO2 sequestration into something real. Okay, and then the last thing, and this is one that I like a lot, actually, it's called enhanced weathering. And what scientists are doing is they're taking that terrestrial waters concept where you produce bicarbonate, and they're trying to accelerate it by making these chemical reactions happen on farmers' fields as they fertilize. There's a lot of promise there. I don't know if it'll ever take off, but it's something for you to watch over these next decades of your life to see which one of these types of human technology end up being successful.